Hi, we are Team DragonBot, and today we will give our final presentation about our SpinVTOL, a novel aerial vehicle. Here are the topics we will be covered today. We will reiterate our overall design goals and give a subsystem overview. We will also discuss the hardware and software methods to estimate heading for properly achieving the spanning takeoff and landing. We then will discuss the simulation and controller design in spanning flying mode. We will introduce an interactive simulation for cruising flight and explain the flight mode transition as well. Finally, there will be a possible future steps we can take as a response to the campus closed since March. In this project, we aim to develop a multi-purpose unmanned aerial vehicle that can achieve VTOL in different terrain. For those who don't know, VTOL means take off and land vertically without a runway. There are indeed many other aircraft can achieve VTOL now, but the thing is they all have mechanisms dedicated to achieving the flight transition, like rotating rotors or actual motors, which are all dead weight when now used. Thus, we want to overcome this and improve the structural efficiency in our design. To achieve the goal, the team came up with 5 preliminary designs. By using the evaluation matrix and taking cruise speed, manufacturability, and ease of control into consideration, we eventually choose the SpinVTOL here in the red box for its simplicity, naivety, and robusticity. Our SpinVTOL design has 2 modes. The cruising mode works like a normal commercial airplane, and the spanning mode is a bio-inspired flying mode that involves the vehicle spanning rapidly around its vertical axis and allows hover, which is impossible for fixed-wing airplanes. Moreover, in our design, all major components are utilizing during the whole flight, and thus can bring the structural efficiency close to 100% and improve long cruising energy efficiency a lot. This is our subsystem overview. We only demonstrate the takeoff process, but the landing is basically reverse all of them. In the bottom left corner, you can see our drone gains enough lift by doing self-rotating. We used rigid body dynamic simulation and some other monocopter concept to verify this. After it has gained sufficient altitude to clear the obstacles, it transitions to cruising flight. The middle part shows the whole routine about how to do the transformation. You can find the cruising mode at top right. We use AVL analysis to validate this as we presented last time. So these are the previous accomplishments. We have our design review and PCB, and this is a test stand we use for avionics validation, and here is our monocopter prototype. So this is our engineering analysis plan. We validated on VTOL mode, cruising mode, and intuitive response to pilot input. And the method shown in the red box is how we approach the goal. The validation methods are actually separated into 2 parts. The physical testing is applied to verify the avionics, while the simulations are used for validating cruising flight in clear view, as well as a VTOL in rigid body dynamics simulation.
Let's start with our validation process of our heading estimation algorithm. Heading estimation is very important because the first step for accurate control is accurate heading estimation. For example, in the SpinVTOL mode, if we want our aircraft to move forward, we'll need to provide an upward force by moving the flap at locations C and D as shown on the screen, and we'll need to apply a downward force at position A and B. The task of the heading estimation algorithm is to tell the avionics where A, B, C, D point is during the flight. If our heading estimation is not accurate enough, the flaps will be moved at the wrong spot, and therefore the aircraft is going to move the wrong direction. To be specific, our algorithm should provide us accurate and consistent heading estimation at any angular velocity that is reasonable. Heading estimation is based on the output of the magnetometer, which is the strength of magnetic field at the x, y, and z direction. We can use the arctangent function to calculate the heading based on the magnetometer reading. The issue here is that the magnetometer is very noisy. The blue line on this graph is the raw sensor data. If we use the raw data to calculate the heading, the noise is going to have the magnitude of about 10 degrees on each side, which is unacceptable. Therefore, we need to implement the filter to smooth the data. We tried the first order and the second order filter. The yellow line, which is the second order filter, is the smoothest. So we decided that we'll use the second order filter to implement our avionics system. We then tested this filter with a sinusoidal magnetometer reading trace. The yellow line, which is the filter data, preserves the sinusoidal behavior while eliminating noises, which means that our filter is performing very well. Our key innovation here is the real-time phase lag correction. The second-order filter has significant lag at higher angular velocity. Here is our basic algorithm of calculating heading. We take the arctangent of our filtered y-direction magnetometer reading over the filtered x-direction reading. So in order to do phase lag correction, we need to extract phase lag. Based on the raw x and y direction reading, we can calculate our raw heading here, which doesn't have any phase lag. And then we can take the difference between our heading calculated with the filter data and the raw data and have the phase lag. However, all the noises are also included in this term. Now we can make the assumption that the SpinVTOL is going to spin in a near constant speed. The phase lag is also going to be near constant. So we can have an average filter on this phase lag and noise term, which will eliminate all the noises and only leave us with the phase lag. Finally, we add this phase lag back to our heading, and we have this corrected heading. So now with the software implemented, we need to test its performance on this test stand, which will simulate the vehicle spinning at different angular velocities. And our validation method here is to light up an LED when the heading is about 60 degrees. And then we take long exposure photos, which will record LED blink within 6 seconds. If the software is performing correctly, the LED blinks should stay in the same place, which is exactly what we observed from these photos, which means that our software is very successful. Our heading estimation is trustworthy, and we can use it for accurate control.
In order to develop and test our control algorithm in auto-rotation, we developed a dynamic simulation. With the airfoil characteristics we previously calculated with Xfoil, this simulation uses blade element theory to calculate lift, drag, and aerodynamic moments. It can also model the effect of thrust and flap deflection. Using a rigid body dynamics, we can simulate the vehicle operation in time domain. This allows us to test our cyclic control with unexpected dynamics effect like gyroscopic recession. The simulation can also produce a rendering with forces thrown for sanity check.
So with the aerodynamics model properly implemented inside the simulator, we proceeded to controller design. And our goal here is to design controller that can stabilize the vehicle and accomplish direction control. We'll be giving our SpinVTOL with target velocity in X, Y, and Z direction, and the SpinVTOL by itself should adjust its motor thrust and cyclic flap to match our target velocity. And we divided our controller design work into two parts. The first is a vertical velocity control, and we are trying to accomplish that by adjusting the thrust. And the other part is horizontal velocity control by adjusting the cyclic flap angle. And in the vertical velocity control, we are implementing two controllers. The first one is the open loop controller, and this one basically maps the motor output with its according desired velocity in Z direction. The second controller is a feedback controller that actually simulates a pilot on the ground. The pilot will be able to sense error in desired and actual height, and therefore adjust the commanded velocity in Z direction by adjusting his or her joystick.
Previously, we established that by applying a cyclic flap deflection as the vehicle is spinning, we can generate a torque that allows the vehicle to move in horizontal plane. We refined this concept and designed a closed-loop controller with feedback linearization to control the rotation axis of the vehicle, namely its direction and magnitude. A tilt to the rotation axis means that the net lift has a horizontal component which can cause the vehicle to accelerate in XY plane. The avionics my teammate just introduced is capable of providing us with the input necessary to estimate the state. Then we can use an open-loop controller to map the tilting direction and magnitude to velocity in horizontal plane. Here we demonstrate the result of our rotational axis control. The row above is a free response of the vehicle without control. The center figure is the magnitude of the inclination. It diverges quickly, meaning that the vehicle will soon tip over. The row below shows the vehicle when we activate the controller and command the rotation axis to stand upright, no inclination. The controller is also stabilizes the disk angle and angle of attack, both critical to successful flight. The periodic oscillation of angle of attack in the bottom right figure is a result of cyclic actuation of the flap, and it is normal. Here we show the result of the full controller. The vehicle is commanded to go right. The figure on the left shows its trajectory, and on the right is an animation. This is good result.
For the cruising flight, though we have done the aerodynamics analysis for the SpinVTOL and get plenty of numbers to prove it meets the requirements by using AVL, we still want to fly the SpinVTOL in the real world to see the result. Since we cannot fabricate currently, the team decided to test the cruising flight by using Clearview RC Flight Simulator. So we want the SpinVTOL could be easily controlled by inexperienced people with using a joystick. In order to customize our design SpinVTOL in the simulator, a new 3D visualization model with movable parts is necessary. As we can see in the right figure, for each movable parts like propeller, flap, elevator, and rudder, there's an objector attached to it. The objector consists of two triangles, and it helps the RC simulator to tell the direction of moving movable parts. One thing should be noted that this is only visualization model, which is not related to the flying dynamics. So here is the physics geometry. It is a simplified SpinVTOL model made up with surfaces. The surfaces of wings, flaps, elevator, and rudders are defined as lift objects, which generates lift and drag. Surface of landing gears and the main body are only generate drag force or drag objects. Thrust objects define the location that generate thrust. However, the magnitude of the thrust is controlled by the motor and propeller, defined in the individual parameter setting file. Coefficient of drags and the lift and mass for each surfaces are also defined in this individual setting file. And here is the flight animation. As we can see, the motor and control surface are controlled by the joysticks, and during the flight, though our pilot is inexperienced and move the joysticks really crazily, the plane is still controlled really well.
Last time we were asked how the vehicle would go from one flight mode to another, and we would like to address this with more detail. Entering the spinning mode from normal cruising is a well-known maneuver called spin entry. To achieve this, the vehicle slows down until one wing starts to stall. When the wing stalls, it generates less lift and more drag. This causes that side to slow down and drop, creating a moment that starts to spin. Then we can apply differential thrust to spin up the spinning and transition to auto rotation. To exit from auto rotation, simply apply thrust to both motors. This allows the vehicle to slow down rotation with drag and gain more longitudinal speed, and the vehicle would follow an expanding spiral. Ultimately, the curvature of the trajectory would be low enough to assume cruising flight conditions.
We identify potential failure modes and their impact on product reliability, and we rank the defects to establish priority. The table in the slide includes top 3 RPM items. First one is the propeller. The potential failure is a crack on it. It may lead to the loss of control and hard landing. It is the failure that is hardest to detect. Our solution of it is to adding a strong, flexible landing gear. The second one is the wing. It might be broken by losing lift and potentially cause overspeed and impact. It's easier to detect failure compared to propeller, and our solution is limiting max spinning speed. The third one is the battery. Due to mechanical damage and overcharge, it might cause fire and explosion, which is the severest failure among all items. Our design controls of it are providing optimized placement and electrical protection, which is important in our system. In conclusion, we finished most of our goals, which are determined in the beginning of this semester. Though we changed some of them due to the reason that we have stayed away from campus and labs since spring break. Those change goals are mostly related to constructing parts. They have been moved to simulating, validating parts, including flights in VTOL and conventional mode and intuitive response to pilot input. As you can see in the previous slides, our cruise mode is validated with AVL, and VTOL mode is validated in simulation. The test stand was built before spring break, and it was validated workable and provided useful information. Inclination control was also achieved and validated in simulation. There were also some improvements that we are not able to do due to the current situation, but can be finished later. They include soft integration, interference testing, and in big picture, environment adaptability and flight mode transition. Thank you for listening to our presentation. Any questions?